Okay, so we have now explored this equation, delta G equals delta H minus T delta S, in pretty decent detail, right? We understand the relationship between the sign of delta H and delta S, and we can use that to predict whether a reaction is spontaneous, right? So in this video, we're going to go ahead and try to put some numbers to this. All right, so before we do this, I want to mention that there's kind of like one special case scenario here, right? So we can make these standard values. So delta G naught equals delta H naught minus T delta S naught. Okay, so it's the same equation, it's just now we're under standard conditions, which means we know that the temperature is equal to 298.15 Kelvin. So anytime you can calculate delta G naught, you can also relate it to this equation using the standard temperature. Okay, so let's see an example here. If we are told that delta H naught is equal to negative 30 kilojoules per mole, and we know that delta S naught equals 45 joules per mole Kelvin. Okay, so our goal is going to be to calculate delta G naught and the equilibrium constant. So we want to calculate both of these two values. All right, so let me point out units here first. So note that the enthalpy is given in kilojoules per mole, but entropy is given in joules per mole Kelvin. Okay, you'll very commonly see that enthalpy and Gibbs free energy both have the unit of kilojoules per mole, but entropy is almost always in joules per mole Kelvin. So the first thing we want to do is convert one of these to either joules or kilojoules. So I'm going to go ahead and convert delta H to negative 30,000 joules per mole. And we do that using our metric prefixes that we've learned in the past. Okay, so we now have delta H and delta S in the proper units. We're under standard conditions, so the temperature is 298.15, so we're able to directly calculate delta G naught. So we have delta H, which is negative 30,000, this is joules per mole, minus the temperature, which is 298.15 Kelvin, times my delta S, which is 45 joules per mole Kelvin. Okay, so let's focus on units for a second. We see Kelvin cancels, so we're left with joules per mole in this term and joules per mole in this term. So these two units add up to give us an energy of delta G in joules per mole. So when we do this, when you plug this into your calculator, you see that delta G naught is equal to negative 31,340 joules per mole, or this would be equal to negative 31.34 kilojoules per mole. So that's our delta G naught. Okay, and now that we know delta G naught, we can easily calculate K because we know that delta G naught equals minus RT times the natural log of K. So again, we're at standard temperature. So this is negative 31,340 joules per mole equals negative 8.314 joules per mole Kelvin times my temperature, which is 298.15 Kelvin, times the natural log of K. Okay, and if we go through here, we'll see that the natural log of K is equal to 12.64, giving us an equilibrium constant of 3.096 times 10 to the fifth. Okay, and hopefully this makes sense to you. We have an equilibrium constant that's very large, right? So it's 3.096 times 10 to the fifth. So we have a very large equilibrium constant suggesting products are favored, and that matches what we calculated for delta G naught. Under standard conditions, we have a spontaneous reaction which tells us products are favored. All right, so that's how we can use our two really important equations, delta G naught equals minus RT natural log of K, and delta G naught equals delta H naught minus T delta S naught. Okay, and these two really are our core equations in this unit. All right, let's try another problem. So draw a line here. In this case, we're told that delta H naught equals 25 kilojoules per mole, and we know our delta S naught equals, let's say, 86 joules per mole Kelvin. Okay, and our goal is to figure out at what temperature will this reaction become non-spontaneous. Okay, so let's first figure out what delta G is under standard conditions. Okay, so under standard conditions, we have delta G naught equals our delta H naught, which is, we'll say 25,000 joules per mole, minus the temperature, which standard temperature, so 298.15 Kelvin, times my delta S naught, which is 86 joules per mole Kelvin. So under standard conditions, the energy of this reaction is equal to negative 640.9 joules per mole. Okay, so under standard conditions, it's spontaneous. All right, so our task is to figure out the temperature when this reaction becomes non-spontaneous. Okay, so that's the transition from a positive delta G, or sorry, that's the transition from a negative delta G to a positive delta G. Okay, and that transition happens when we go through zero. Okay, so in this situation, we have a positive delta H and a positive delta S. So in this reaction, the delta S is favorable, right? Positive delta S is a good thing. Positive delta H is a bad thing. So increasing the temperature will increase the contribution from our favorable entropy. So at high temperatures, so at large T, we expect this to be spontaneous. At low temperature, we expect this to be non-spontaneous. So when we calculate the temperature when the reaction becomes non-spontaneous, we're going to expect it to be below the standard temperature. Okay? So the switch comes when delta G equals 0. Okay? So the transition from a spontaneous reaction to a non-spontaneous reaction happens when the reaction is at equilibrium, and that's when delta G equals 0. So in this case, our delta H is 25,000 joules per mole. Our temperature is unknown, and our entropy is 86 joules per mole Kelvin. Okay, so we arrived at the fact that we want to know the temperature when delta G is equal to 0. That's the temperature at which the reaction switches from being spontaneous to being non-spontaneous. And once we arrive at that conclusion, then now it's just a matter of plugging our values into our equation. Okay, so when we do this, we can solve for T, right? So this is going to end up being negative 25,000 joules per mole equals negative T times 86 joules per mole Kelvin. And we can solve for our temperature, and this is 290.17 K, which corresponds to 17.55 degrees Celsius. So just as we predicted, the reaction is becoming less spontaneous as we decrease temperature. Okay, so that's two ways you can use this equation, delta G equals delta H minus T delta S. There are lots of others, right? So the important things to keep in mind and to think about is just understanding what the variables are, what you know, and what you need.